Our lab today will be about open channel flow. In this lab, we are going to demonstrate the concept or the applicability of continuity and Manning equations to describe the uniform flow. We are going to use teaching recirculation flume. It is 5 meters in length and its width is 76 millimeters and it is 250 millimeters height. And there is a main component that we are going to use a lot during this experiment, which is the screw jack, which we are going to use to modify the slope of the flume. Okay. The background that we are going to build on is the Manning equation. Manning equation can describe the uniform flow, and the flow also should be steady. We already dealt with steady flow before, which means that the flow does not change with time, the flow constant with time. And what I mean by uniform flow is that the slope of the surface, the slope of the water surface equals the slope of the channel bottom. So just imagine that by looking from the side to the flume that we are going to use during this experiment, it looks something like that. It has a certain slope, and when there is a flow or when there is water flowing inside this flume, it should look something like that. And when I say uniform flow, I mean that the slope of the water surface is equal, or in other words, is parallel to the slope of the bed. And I will show you that in a while during the experiment, and I will also show you the cases when the flow is non-uniform. So taking that aside, let's focus more on Manning equation, which we have it here. Manning equation says that the water velocity u equals 1 divided by n multiplied by r power 2 over 3 and multiplied by the square root of S naught. So the U is the velocity in the metric units, meter per second. N is something called Manning roughness coefficient. And just to let you know, in this experiment, our objective will be how to measure or determine the Manning roughness coefficient for different materials. S naught is the channel slope that can be adjusted, as we said before, and R is the hydraulic radius. And the hydraulic radius is a simple relation between the area and the water perimeter. So that was the side view of the flume. So just imagine that we are looking from the front. The flume will look something like that. It's a rectangular flume, and just to make that more clear, in the lecture, Dr. Abu Kifa showed you the typical cross-section of the channels. It was something like that, right? So in this case, our channel isn't trapezoidal, it is a rectangular channel, and the water surface should be inside this section. Let's say that it's in this location. We already said that our flume has a constant width, which is 76 millimeters. And based on the flow inside the flume, we can easily calculate, or we can easily measure the value of water depth y. So once you have the water depth and the section width, you can calculate the area easily, right? By multiplying the width, which is called in most cases small b, by the value of y. What about the water perimeter? As the same says, it's the perimeter of the section that is wetted, or the section or the perimeter of the section that touches the water. So basically it will be the length starting from this point up to this point. So by knowing that, the water perimeter will equal the bed width plus twice the water depth. Is it clear? Great. So if we are going to use, in this experiment of course, we are going to use the SI units. So Manning equation will be as it is. But just in case you are working with English units, you should replace 1 to 1.49, and of course instead of meters you will use feet. Great. So here is also another form of Manning equation. Equation number 3 is almost the same as equation number 1. The only difference is that I have multiplied both sides by the area. So just to let things become clear, if I multiplied the right and the left hand side by area, the left hand side will be UA, which I can substitute with, can you tell me? Q, exactly, will equal 1 over N area or 2 over 3. I just prefer to write it as square root of the square root of S naught. So what is the purpose of converting Manning equation from this shape to that shape? The reason of doing that is in some cases we will need to calculate the normal flow depth. And actually this is the advantage of Manning equation, that it can tell us what is the normal depth for a certain geometry and a certain discharge. So in case you have a channel with N Manning roughness coefficient, and there is a discharge with a value of Q, and of course you know the slope, you can calculate the normal depth. And because the solution of this equation isn't straightforward, I'm going to come back to this equation and explain how we can really get the value of normal depth from this equation. Any questions at this point? Great. So we already said that applying Manning equation can only be done if the flow is uniform and steady. Of course, the flow that we are going to work with is always steady, I mean in this lab, but in some cases it can be non-uniform. And in these cases, when we have weave or slow skate, these two tools or these two equipments are commonly used to control the flow, to get the discharge for a certain channel. But just to let you know, when we have weaves or sluice gate or actually any change of the channel geometry, we can't use Manning equation. And instead, we can use another equations or another tools to know the discharge, which I will explain later. Equation number 4 and number 5 are very important during our experiment. I think Dr. Abu Kefa will describe and explain that later in the lectures. But these two equations were used to drive this equation here, the wheel equation. Wheel equation, or the wheel itself, is used to calculate the flow rate or the discharge for a certain channel. And that equation says that the discharge Q equals C B H power N. So let's see each variable in this equation, and let's start by B. It says here that it's the width of the wheel, and wheel actually is a very simple tool that looks like a box, as you can see here in this schematic figure. We are going to use something called broad-crested weir. It has different shapes. The one that we are going to use is the broad-crested weir, and it is basically, as you are going to see in a while, is a simple box, but the actual weir has a rounded edge, something looks like that. So regardless of the shape of the weir, the equation has also the h variable, which is the upstream head above the crest. This variable here, it only starts from this point to this point, and you should differentiate between h and the water depth, which is this depth here. So if you have the water depth, you can subtract the width, or the height of the weir from the water depth to get the value of h. N is the exponent that will be 1.5 in our case, and C is a constant that accounts for the difference between the measured and the actual flow. If you recall lab number 5, when we were using different tools to calculate the flow rate, we used the Better tube, the Venturi tube, and can you tell me the third one? Yeah, that was a very long time ago. It was the nozzle meter. We calculated the C coefficient, and actually in this situation, the C coefficient is almost the same. It is a factor, or it's a constant that takes into account the difference between the actual flowing discharge and the discharge that we can calculate using this equation. And in today's lab, we are going to figure out the value of this constant based on the measurements that we are going to take. So before going any further into the procedure itself, let me explain two things. The first one is how we are going to calculate the water depth, and the second thing, the concept behind our experiment. We said that we are going to calculate the value of n, but if you reach this position, it says here that we will do the experiment 4 times for 2 channel roughness coefficients and 2 different slopes. There is nothing hard about the slope because we can adjust it easily, but the only thing I want to consider is the value, or I want to explain is the value, what I mean by 2 channel roughness. To do that, let me first explain the components or the shape of the flume that we have here. Our flume is a very simple rectangular flume, and for a certain discharge, the water level will be in a certain position like that. The flume we are using is composite, which means that it consists of different materials. Let me close the door first. Can you close it, please? Thank you. So the cross section that, or the channel that we are going to use, is a composite channel which has different materials. In our case, the material of the bed will be metal, while the side will be glassy. Or glass and metal, glassy and metallic. Great, so this means that while the water flows inside this section, it is affected by the friction between the three sides, right? Because when we were dealing with the pipe flow, we said that if this is the pipe and this is the water inside, there's like water inside this pipe, at the very far points, the friction with these pipes is the maximum, so the flow or the particles of water is not moving, while in the middle, because the friction is very small, this is the location of the point of water that moves very fast. So if we want to draw a profile for the water velocity, it will look something like that, right? We explained that before already. The same case applies here. This part of the water section is affected by the friction with the glass, while this part here will be affected by the friction of the metal. And can you guess which friction should be higher? Which friction coefficient should be higher for metal or glass? Metal should be higher. Who agree with that? Yeah, this is right actually. Metal will be more rough, so I think, or so I understand that the Manning coefficient for the metal will be higher than the Manning coefficient for the glass. But anyway, because we are going to use Manning equation, we are going only to use one value for the Manning coefficient, which is the equivalent Manning coefficient for the whole section. So when I say true roughness, I mean that in a certain point, we are going to replace this metal bottom with another bottom that is gravel, which we are going to see in a while. And of course, if I asked you which roughness will be higher, the roughness of the metal or the roughness of gravel, you will say, which one do you think will be more rough? Of course, gravel will be higher. Maybe you can't like imagine what I mean by gravel. You will see that in a while, but once you see it, you will understand that, of course, this surface is very rough compared to the metal. Great. So at this point, you understand the concept behind the roughness of the bed. And the second one, or the second concept that I want to explain before going any further with the experiment, is the way that we are going to calculate the water depth. So I brought the point gauge that we are going to use during our experiment, and I think it's a good way to open the camera and show it to you. It will be much easy to show it to you instead of so okay, so the point gauge consists of different components. It has this slider ruler. It's a very small ruler, and it has this fixed ruler that does not slide, and we have this screw that can hold the slider from falling down when it's locked, and of course we have this point that will be inserted or should be coincided with the water surface. Great. So why we use this point gauge instead of using like a regular standard ruler? The reason is that using this point gauge can give us a more accurate measure, and you will see that in a while. So just imagine that for a certain discharge, when we try to measure the water depth, the slider was at this position. What should be the reading? To get the whole number of the measurement, it will be basically the same as the regular ruler. You will check the position of the zero. In this case, the zero is at 60 something, right? Should be 64 or 65, right? So using a regular ruler, you won't be able to get the actual degree or the actual number or the actual first digit, let's say. You will just guess, okay, it's between 64, 65, so I will take it 64.5. But in this case, this task will be much easier because you can get the first digit by making a very simple trick. You will see which line in this small ruler will coincide with any line with this long ruler. Of course, you won't be able to see that in a while, but in case you understood the idea, I will make a very simple sketch that will show it to you. So you got the idea, right? To get the whole number, you will check the position of 0, and to get the first digit, you will do this trick that I'm going to show it to you right now. So if this is the fixed ruler, and just for example, in our case, it was showing here that this is 60 and here is 70, and in between these two numbers were very fine marks that represent the millimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And for the smaller ruler, it was something in between 34, something between 34 and 35. So let's say that it is in this location. And that was the 0. And we have here 1, 2, 3, 4, and 5 up to 10. So because we have the 0 here, we know that the first or the whole number is 64 point something millimeter, right? So the way you can get the first digit is to check which line in the smaller ruler will coincide with any line with the tall or the long ruler. In this case, the first line does not coincide, the second the same, but here the third line coincides with a certain line in the long ruler. And because this line is the 3.3 millimeters, so the measurement in this case would be 64.3 millimeters. This is a very easy trick that you can use to actually get a very accurate measurement. Any questions? Great. So That was the second thing I wanted to explain, and I think we can go to the procedure right now to see the way that we are going to conduct our experiment. Third thing is that you will fill the reservoir. Of course, we have the pump that will push the water from the tank or from the reservoir, so we'll have to fill the reservoir first. For the first experiment, we will set the slope to 1%, and before doing anything, we should turn on the pump, open the flow control valve, and after doing that, we will get our first measurement, which is the mean flow rate. And by doing that, you should consider using the units of meter cube per second, because what we are going to get during the experiment is liter per second, so you should consider converting it. And the way that we will measure the flow rate will be using the calibrated basin and the stopwatch. We already did that in one of our labs before, so we'll use the same concept. After having the discharge, we will measure the depth, and after doing that, we will repeat this experiment again, but with 1.5% slope. After finishing the second experiment, we will get back the slope of 1%, but we will insert a different bed material, which in this case will be gravel tiles that you are going to see in a while, and you will have to repeat the same procedure again. That's why we are going to make 4 trials, 2 in each experiment. 2 experiments, and each experiment has 2 trials. While for the real experiment, you of course will have to remove the rough bottom inlays and put the wheel. You will set the slope to 1.5%. You will repeat step 2 and 3, which is in this case, you will record the flow, then you will record the depth. After doing that, you can turn off the pump and make your calculation easy. Great, so any questions? Yeah. Yeah, of course, I will get into that right now. Okay, let's speak about the worksheet. The first experiment has 2 trials. The second experiment has also 2 trials, and both of them is the same or are the same. The first thing will be to calculate the flow rate, measure the flow rate, measure the flow depth. Area can be calculated, diameter can be calculated, and the hydraulic radius will also be calculated. So what can be done for the value of u? Can you guess, or can you tell me how we are going to calculate the velocity? Great, this is correct actually, because we only have 2 options up to this point. We can calculate it from, I'm not sure why this is happening. So at this point, you can calculate the value of y from 2 equations. The first one is by dividing Q over area. The second one is by getting it from Manning equation. right? If you recall, Manning equation has Manning coefficient in it, and I think you understand that there is no mention for any Manning coefficient right now. It's not given. And actually the purpose of this experiment is to get Manning coefficient. So the first step will be, or at this point, we will have to calculate the Q, or the velocity, using this equation. Yeah. I'm sorry, but I can't hear you clearly from the mic.
We're going to estimate the Manning coefficient, right? So that's why we use Q over A.
Exactly. So after calculating the value of U from Q over area, we can easily sub in Manning equation that says U equals 1 over N area, hydraulic radius, power 2 over 3, square root of S naught. Because at this point, you will have U, R, S naught, and you can easily get the value of Manning, right? Great, so you will do that for the first slope, and you will also do the same for the second slope, and you will calculate the average Manning coefficient, and this will be the Manning coefficient of the flume. So I just want you to tell me if you think that the Manning coefficient should change or shouldn't change with the slope, based on what you understood and based on what you know about Manning equation. Yeah. So you say that when the slope increases, Manning coefficient will decrease? Great. So let's get back to Manning equation and see. It should stay the same. This is the exact thing that I was looking for. Manning coefficient shouldn't change based on the slope, because it is only dependent on the material of the surface, which in this case won't change. But there is a very trick thing here that you should consider. Your answer was great actually, but the actual situation, Manning coefficient for this experiment or for the flume that we have here should change. Should change, yeah. No. If you wrote that it shouldn't change, your answer was correct. But the reason that it will change here, not because it depends on the slope, because it depends on material. And let me explain that so you understand the dilemma behind it should change or not. Like 5 minutes ago, I said that we have a composite section, right? And what I meant by a composite section is that the material of the bed is different than the material of the side. Okay, great. So just imagine that for the first experiment, the water surface was at this location. Right, so this is for the first experiment, the first trial, at S equal 1%. Based on that, where do you think the location of the water surface for the second experiment when we increase the slope to 1.5%? Should it be higher or lower than this line? You say lower. Who agree with that? Can you explain that for me? You're right. It depends on, this is related to the velocity, exactly, because when you increase the slope, you are allowing more water to fall more quickly, because actually Manning equation like describe the relation between the driving force, which is the gravity, and the resisting force, which in this case is the friction. So when you increase the slope, the gravity component will be higher, so the flow will be accelerated. This means when the velocity increases, what will happen to the area? It will decrease. And because we have a limited width, the water depth will decrease. And for the second experiment, the second trial, the water surface will look something like that. So regardless the location of the water surface, let's think a little bit about the Manning coefficient. Conceptually, should it change or not from case 1 to case 2? I will give you a tip and then I will ask you if you get the idea or not. The tip is, think about the contribution of each side in the two cases. I mean, you have 3 sides, 2 glass sides and 1 metal side. The contribution of each side will change, or it won't change for the 2 cases. In other words, for the bed, it will always be the same width because it's constant, right? This length here won't change from case 1 to case 2, right? So the contribution of the metallic side will be the same. So the friction that this side is putting into the water section is constant from the first and the second, constant in the first and the second section. The second trial. Okay, what about the sides? Does it stay the same, or does it change with time, with trial? Of course it changed, right? Because in the first trial, that was the length that is in touch with water. But for the second trial, this is the length that is in touch with water. I mean like twice this length, because you have 2 sides. So does that show you anything for you? Does that explain why it should change? Yeah. That's right, because it is related to the material, and because we have 2 different materials, actually the Manning coefficient will depend on the material and also the condition of the water level. If you have like 3 sides with the same material, like regardless the position of the water, it will always be the same Manning, because the same water is touching the same material. But because here we have a very specific condition, it's not the same. So your answer was correct, but it wasn't accurate in our position. Great, so that was the idea that I wanted to explain. And before making the experiment, there is this weird experiment here. Same as before, we will start by calculating the flow rate. Measuring the flow rate, measuring the upstream flow depth. And because we are only interested in the head above the crest, you will subtract the value of the weir height from the water depth to get the upstream head. Understood? After doing that, you can sub in the wave equation to calculate the discharge coefficient. So, getting back to the question you asked, here we have the normal flow depth question that I said we will get back into it at the end of this experiment. Just so how we are going to calculate the normal depth? It gives you here the slope, the flow rate, the estimated Manning coefficient from the previous experiment. The first step will be to calculate the right-hand side of equation number 3. So let's get equation number 3 from here. Great, so what does I mean by the right-hand side? It's basically this term here, because you already estimated the Manning coefficient. It already gives you the Q and the slope. So just for example, let's say that after doing this simple calculation, the value of the right-hand side was equal to 0.0008. I'm just guessing this number. Great, so where is the normal depth? Where is y in this equation? Can you tell me? Where is y? Of course, the area depends on y. I have already said that the area equals B multiplied by y, and also the R is a function of y and B. So to simplify the left-hand side, we can write it in this form: by multiplied by by divided by b plus 2y, and don't forget the power. Easy? Okay. We already have y here, it is 0.076. So the equation now will be this term equals 0.0008. So how do you think we can solve this equation that is implicit in y? I mean by implicit that you can't convert this equation to something like that. You can't say y equals something. What is the other way that we can solve this kind of equations? Iterations? Exactly. So you will do some iterations. We call it trial and error. There are like many ways to do it, but the easiest way is to use the trial and error concept or approach. And what I mean by trial and error is you will start by assuming a certain value for y, check the right-hand side. Let's say, of course, y can't be negative, so the smallest value for y is 0, so let's just take it as 1 millimeter. You will sub in the left-hand side. Of course, the right-hand side won't be 0.0008, so you will continue doing that until you reach the value that has a right-hand side of 0.008, and it shouldn't be exactly the same as the right-hand side. If it is close to that value, it will be green. So this is the way that you are going to calculate the normal depth in this experiment. But actually, I would like to teach you a very simple trick that you can use to deal with this kind of equation, that you can't easily get the value of a certain variable. If you have a calculator, same as mine, it is Casio FX991. I think many variants of this Casio calculator can do this trick. So I will open the camera again to show you how to do that. And this trick will be very useful in case you have a very limited time, because of course trial and error might take forever, and after that it might not reach the actual or the correct solution. So what I recommend is, in case you are very confident of what you are doing, you can use the calculator. And I am saying very confident because in case you use the calculator and the answer wasn't correct, you won't get any portion of the mark, because the advisor or the corrector won't be able or won't understand that you used your calculator. But in case you made the trials, of course he will give you like a portion of the mark, right? So let's try to solve the equation that we have using this calculator. What I will do is simply to write the equation first. So our equation is 0.076, which is the value of P, 0.076 multiplied by the variable Y. I feel more comfortable using X as a variable instead of Y, so I will just press this alpha here and press the X button. So this is the variable X, or in our case, the normal depth. And this is multiplied by the same term, 0.067x, divided by the weighted parameter, which is the P, 0.076 plus twice x. And don't forget to put the power. And all of that should equal, and I will add the equal sign by pressing the alpha and this button here. This should equal 0.0008. So now I have my equation written, and what I want is to get the value of x. To solve the equation, you will press the shift, this button here, and it will say, do you want to solve for x? Of course I do. And what it actually does is the same as you are doing in the trial and error approach. It asks you for the first guess, just in case you know the approximate value of y. And of course we don't know it, so I will accept the 0 as the first guess. There should be an equal sign here, but it's a very old calculator, so I will press here. It will take maybe like 5 or 7 seconds, and it will directly show you the answer. And here's it. The x value, in our case the normal depth, will be 0.11 meters. Make sure that you are using the correct dimensions, because this can mess all your calculations. Great, so that's it for the explanation part, and let's go and make the experiment and take the measurements that we have. Any questions?